Hello, this is Bill Levinson with Levinson Productivity Systems. Thank you for listening. This is part 4 of Principles of Green and Sustainable Manufacturing. The previous section discussed methods for seeing waste of material, energy, and so on that often hide in plain view. This section will discuss something called the control surface approach and material and energy balance approach for doing this. The control surface approach is very characteristic of chemical engineering. Actually, most chemical engineering students learn this in the freshman or sophomore year. And what you do is you draw a control surface around a process, and you have material inputs and material outputs, and they have to balance. Just like an accounting statement, everything has to balance. All the material that goes in has to balance with the material that comes out. All the energy that goes in has to balance the energy that comes out. And this analytical approach actually gives material and energy waste absolutely no place to hide. We said in the last section that we didn't think too highly of the carbon footprint as an energy consumption metric or an energy waste metric, because there's plenty that the carbon footprint can overlook that simply cannot hide from a control surface and material and energy balance approach. We said material and energy balance is similar to debit-credit accounting. Everything has to balance in both quantity and kind. Materials have to balance by weight and identity, and energy also has to balance. Here's a qualitative example of a material and energy balance. You have a power plant, you have a fuel such as coal, oil, or gas, and also you have to add air to burn it that goes in. Now everything that goes in has to balance with what comes out. What comes out, you can see smoke or probably steam coming out. And when you do an analytical balance, you'll find that most of what's coming out is nitrogen. Now, if people are fixated on carbon dioxide, they're going to overlook the nitrogen, which is actually carrying a lot more heat up that stack than the carbon dioxide. The nitrogen is carrying the value of your fuel up the stack, and that kind of waste is invisible to a carbon footprint metric, but it's forced to become visible by a material and energy balance. Now, the fact that the nitrogen does this is a theoretical argument for burning the fuel with pure oxygen. On a practical level, the cost of the oxygen and also the cost of the equipment necessary to contain the kind of temperature that would produce could be practical obstacles, but that's the kind of thinking that the material and energy balance would lead to. Also causes one to think about fuel cells, which end up bypassing some of the thermodynamic efficiency limits on ordinary combustion. We saw this one before. If you look at what goes into the process, a certain weight of metal to make this part, and then you do a systematic balance on what comes out, you'll see how much the parts weigh versus how much the metal scrap weighs. That forces the metal scrap to be visible. Under ordinary circumstances, if you don't do that, the metal waste is taken for granted. The workers get used to it. It becomes an accepted part of the job, and nobody ever looks for a better way to do the job. Material and energy balance forces the waste to become visible. We published a paper in the Apex magazine on something called a bill of outputs or bill of products. Everyone knows what the bill of material is. It's a list of everything that has to go into the manufacture of the products. A bill of outputs lists everything, not only the product, but also everything that's thrown away in the process of making the product, again forcing material wastes to become visible. Dumpster diving means going through everything the plant throws away. Some people actually go into their dumpsters to see what's in there. Question is, where does it come from? Use the 5 whys technique. Why is it made? Why is it discarded? An example where Henry Ford saw the rust in the pile of slag, thereby noticing that actually iron was being thrown away with the slag. was an example of dumpster diving. Okay, what's wrong with this picture? This is a cleaning process typical of semiconductor wafers, perhaps also metal parts. You have dirty parts going into a tank, water's going in and out, then the parts go into a second tank, and clean parts come out. Can anyone see anything wrong with this product? By the way, if you do a control surface on this, it accounts for the water that's going in and coming out having to be treated, say in the deionized water plant for reuse. Now, before we go on, does anyone see anything wrong with this picture? How about making the water work twice? You have counter-current flow. You're using only slightly dirty water from the second tank to clean the extremely dirty parts in the first tank, and you're using half as much water. Your water treatment plant has to do only half the work. You end up saving a lot of money there. Okay, waste in machining. Given 5 aluminum billets, suppose you have a process that converts 1 billet into parts, grinds the other 4 into scrap to be sent back for recycling. As I said, when we look at these examples, the joke about underachievers or perhaps your company's competitors putting in a light bulb by having one person hold the bulb and 3 or 4 turn the ladder is not very funny when you look at how the processes actually work. There are actually machining processes that do exactly that. As a matter of fact, we read an article maybe 10 or 15 years ago in a manufacturing engineering magazine about a company that bragged about having a very powerful aluminum machining tool that would grind billets into scrap. Well, the idea is to make parts and not grind the billets into scrap to be recycled. We understand, of course, they had to grind off the aluminum to make the parts, but as we showed earlier, Henry Ford looked for ways to avoid the need to do that much machining. If we look at our definition of green manufacturing, 1 billet of aluminum is non-negotiable with the laws of nature because that billet comes out as parts. The other 4 billets are waste or muta, and that obviously is negotiable with the laws of nature, and one does that by redesigning the parts and or the process to reduce the amount of machining. Now, the Ford Motor Company, a process that converts even 25% versus 80% of the stock into swarf or chips got attention, and the workers found a way to reduce this to about 2%. Incidentally, the problem of machining the stock into scrap was noticed as early as 1915. A book by Arnold and Perot talked about a product made at then it was the Highland Park plants, and they talked about the amount of metal that was machined into chips as opposed to being made into parts. Okay, that's the end of this section. The next section we'll look at some examples of green manufacturing. Thank you for listening.